Hello, my inquisitive friend, and a very warm welcome to the Deepfield channel. Tonight, we're going to set off on an expedition unlike anything you have ever experienced, not across a geographical map, but deep into the fabric of time itself, venturing into the oldest and most tranquil layers of the universe, where every single star you have ever gazed upon is merely a solitary grain of sand on a shoreline stretching far beyond the limits of human imagination. This is a journey through the profound epochs of the cosmos, and I promise to do my best not to make this awe-inspiring topic so stimulating that it completely robs you of your sleep. Before we begin our voyage, I would love to know in the comments which corner of the globe you're tuning in from tonight. And if you are feeling too lazy to type much, just drop a simple hello. It might seem like a minor detail, but this small action signals to the YouTube algorithm that our community is a welcoming haven, helping us attract more weary minds looking to unwind with us. If you enjoy our scientific expeditions, please leave a like and subscribe. And to those of you who are already part of our community, thank you so very much. If you wish to feel even more connected, please consider becoming a channel member. Members are granted early access to our videos before anyone else gets to see them. You can find the link right down in the description. Now, wherever you happen to be, find a deeply comfortable position for your body. Let your shoulders drop and sink into the surface beneath you. Unclench your jaw. If sleep decides to visit you during this journey, gladly accept its invitation. Let us begin. There is a specific experience that nearly every human being has encountered, yet very few ever pause to examine it closely. It is that exact moment when you are lying in the dark, gazing upward, and you suddenly realize that the night sky is not merely a decorated ceiling. There is a presence up there that pulls at you, that beckons, causing a strange sinking feeling in your chest, as if your physical body comprehends a truth that your conscious mind is still struggling to put into words. You have felt this before. It is that abrupt sensation of insignificance, the realization that the ground beneath you is just a fragile shell drifting through something unfathomably vast. Well, that feeling is not anxiety. It is a profoundly accurate instinct. It is your nervous system reacting to a fundamental reality that science has spent centuries attempting to quantify. What we refer to as the cosmos, the observable universe, or simply space, is not merely a large location. It is a grand stage where the very concept of magnitude loses all meaning. And what is even more mind-bending is that this stage has not existed for eternity. It possesses a history, a narrative with a distinct beginning, an ongoing evolution, and a trajectory that surpasses anything the human mind can naturally intuit. We are discussing the deep time of the universe, which is perhaps the most quiet yet explosively profound concept that science has ever generated. To begin grasping the concept of deep time, we must first dismantle an illusion we have carried with us since childhood. When we gaze at the night sky and spot a star, we get the impression that we are observing something that exists right now in this very instant, much like looking at a lit lamp across the room. But that is not what is actually happening. The light reaching your eyes departed from that point in space a vastly varying amount of time ago. Some stars visible to the naked eye are dozens of light years away, others are hundreds. The closest star to our Sun, Proxima Centauri, is just over 4 light years distant, meaning the light you would see from it tonight left its source over 4 years ago. You are not witnessing the present, you are looking at the past. The entire night sky is essentially a museum of bygone moments. This characteristic of the universe, where looking far away is synonymous with looking back in time, is known as light travel time, and it is so profoundly counterintuitive that even seasoned physicists must pause to truly absorb it. Consider this. If an alien civilization existed on a planet 1,000 light years from here and pointed a sufficiently powerful telescope toward Earth, they would not see you. They would see what our planet looked like a millennium ago. They would observe untouched forests, oceans devoid of political borders, and perhaps the smoke of medieval campfires rising from villages that are now nothing but archaeological ruins. In the cosmos, the present is a concept that only exists on a strictly local level. Now let us expand on that thought. On the most distant galaxies we can detect with our most advanced telescopes are situated at such staggering distances that the light we capture from them travelled for nearly 13 billion and 400 million years before finally reaching our instruments. Not 13 years, not 13,000, 13 billion. And the story this ancient light tells us is of a universe completely unlike the one that exists today. It speaks of a young, dense and scorching hot cosmos, where the very first structures were just beginning to coalesce in a darkness that was barely being pierced by the ignition of the earlier stars. This represents the first major step into deep time, and it is already enough to induce a sort of gentle vertigo. But let us continue our descent. The universe has an age that modern science can estimate with astonishing precision. Roughly 13 billion and 800 million years. This is what we refer to as the cosmic time elapsed since the Big Bang, the precise moment when space, time, matter, and energy began to exist in the forms we recognize. However, this is also where one of the most widespread popular misconceptions about the cosmos lies, and it is worth carefully untangling it. The Big Bang was not an explosion that occurred within a pre-existing empty void, as if someone had detonated a bomb in the middle of a dark room. That mental image, while poetic, is fundamentally incorrect. The Big Bang was the expansion of space itself. There was no outside for the explosion to happen in. There were no edges expanding into a vacuum. All of space, at every single point simultaneously, began to stretch and expand. Imagine taking a lump of raisin bread dough and placing it in the oven to rise. Every raisin moves away from every other raisin, not because the raisins are swimming through the dough, but because the dough itself is expanding between them. The universe operates in exactly this manner. Galaxies are not flying through space away from one another. The space between them is simply growing. This expansion is continuous. It was incredibly violent during the earliest moments, and it is still happening right now even as you breathe. The revelation that the universe is expanding, made in the early 20th century by astronomer Edwin Hubble through his observations of distant galaxies, completely turned upside down the human perception of an eternal and unchanging cosmos. If the universe is expanding right now, then it must have been smaller in the past. And if you mathematically rewind the clock far enough, you reach a point where all the matter and energy in the cosmos was compressed into a state of incomprehensible density and temperature. Not something the size of a dust grain, not something the size of a soccer ball, but something that classical physics cannot even begin to describe adequately. A state where the laws of space and time as we understand them simply cease to apply. There is a persistent myth claiming that the universe sprang into existence from absolutely nothing. This is a gross oversimplification that obscures more than it illuminates. What physics actually tells us is that the initial singularity, that extreme state from which everything emerged, cannot be described by our current physical models. There is a hard limit to where our equations remain valid, known as the Planck time, which corresponds to roughly 10 to the power of minus 43 seconds after the very beginning. Prior to that infinitesimal instant, the physics we know offers no answers. This is not because science is ignorant, but rather because the mathematical tools we use to describe reality hit their absolute boundaries. The nothingness from which the universe supposedly arose is, in the best possible interpretation, a quantum state of energy fluctuations, not a literal absence of everything. But let us return to what we do know. The cosmos we inhabit possesses a distinct structure. It is not a uniform sea of randomly scattered matter. The observable universe, which is the portion of the cosmos whose light signals have had enough time to reach us since the dawn of time, spans a diameter of about 93 billion light-years. That number alone demands a moment to catch your breath. 93 billion light-years, and keep in mind that the universe is only 13 billion and 800 million years old. How is it possible for the observable universe to be larger than the distance light could have travelled in that time frame? Precisely because space itself has expanded. regions that were once close enough for their light to reach us have been carried far beyond our observable horizon by the very stretching of space. Within this observable universe, there are structures that defy any intuitive human sense of scale. Let us start with galaxies. It is estimated that there are somewhere around 2 trillion galaxies in the observable cosmos, although many are too small and faint for our current technology to detect. Every single galaxy is a gravitationally bound collection of stars, gas, dust, and dark matter. Our own galaxy, the Milky Way, harbours anywhere between 100 and 400 billion stars, depending on the counting criteria and the latest methodologies. This is a number the human mind cannot visualize directly, but we can attempt to grasp it indirectly through an analogy. If you tried to count the stars in the Milky Way out loud, at a pace of 1 per second, without ever stopping to sleep or eat, it would take you somewhere between 3,000 and 12,000 years to finish, depending on whether we use the most conservative or the most generous estimate. 3,000 years. That means if you had started counting when the very first pharaohs of ancient Egypt were building the pyramids, you still would not be anywhere close to finishing the task today. The stars within galaxies are not distributed evenly. They arrange themselves into spiral arms, flattened disks, spherical halos, and globular clusters that orbit the main galaxy like satellites. Our Sun is located in one of the outer spiral arms of the Milky Way, at a distance of roughly 26,000 light-years from the galactic centre. And right in the middle of most large galaxies, including our own, resides an object of singular nature and colossal mass. A supermassive black hole. The one in the Milky Way, known as Sagittarius A, possesses a mass equivalent to about 4 million times that of our Sun. But galaxies in turn are not isolated entities. They organise themselves into groups and massive clusters. The Milky Way belongs to what we call the local group, a collection of over 50 relatively nearby galaxies, of which Andromeda is the most prominent aside from our own. This local group is itself a component of a supercluster named Laniakea, a structure of such immense dimensions that any attempt at an everyday analogy becomes almost comical. Laniakea stretches across about 500 million light-years and contains the mass equivalent of 100,000 galaxies. And Laniakea is merely one among many similar structures populating the observable universe. The largest scale structure of the cosmos curiously resembles something you might have seen before, a sponge or the internal crumb of a bread loaf full of holes. Filaments of matter, primarily composed of dark matter and gas, form walls and webs that intersect at dense nodes called superclusters, while between them lie the cosmic voids, immense regions with very few galaxies where space is, by comparison, almost entirely empty. This cosmic web, as it is known, is the largest known structure in the universe, and it emerged from the minuscule quantum fluctuations present in the very first instance after the Big Bang, which were then amplified by gravity over billions of years. Here is a fact that deserves a moment of silent contemplation. The irregularities you observe in the cosmos today, the galaxies, the filaments, the voids, all of this grew out of density variations that were smaller than 1 part in 100,000 in the primordial universe. The difference between where a galaxy exists today and where a void exists today was, at the very beginning, almost entirely imperceptible. Gravity, working with infinite patience over billions of years, amplified these microscopic differences until it sculpted the monumental structure we see today. It is as if you had a slightly crumpled sheet of paper, and that gentle crumpling had grown, driven by an invisible and patient force, until it became the towering Andes mountain range. And this brings us to the very heart of the question that deep time poses to us. Everything you see, everything that exists, from the subatomic particles inside your cells to the vast tapestries of galaxies stretching across hundreds of millions of light-years, all of it emerged from an extremely simple and intensely hot initial state. It was shaped by forces that operated with incomprehensible patience over timescales that human experience simply lacks the tools to feel directly. The cosmos is, above all else, an ongoing process. It is not a static stage where events merely take place, but a dynamic entity in constant motion and transformation, possessing an infancy, a youth, and, as physics suggests, a distant, cold destiny that lies far beyond the reach of any living being in existence today. And within this grand process, there is something that deserves far more than just fleeting admiration. There is something that demands the oldest and most genuine question any mind could possibly formulate when faced with the cosmos. Where does the energy that animates all of this come from? Where does the force originate that has kept the stars burning for billions of years, that sculpted the galaxies, that warmed the planets, and that eventually, in an obscure corner of an ordinary spiral galaxy, produced the exact conditions for something like life to emerge and, ultimately, look up at the sky with eyes capable of recognizing the vastness that created them? This oldest of questions was never spoken aloud. It arose long before the invention of language, long before the mastery of fire, long before the creation of any scientific instrument or method. It manifested in the form of a sustained upward gaze, a being that stopped, tilted its head, and stood there, motionless beneath the night sky, sensing that something monumental was happening above without understanding why those lights were there, why they always returned, or why they never burned out. The question was pure, raw intuition. Where does all of this come from? What fuels this grand spectacle? What sustains the glow? For the vast majority of human history, the answers provided were purely poetic. The sun was driven across the sky by a chariot. The stars were pinpricks in the great mantle of the heavens. The cosmos was upheld by divine will or by grand personified forces that loved, fought, slept, and woke. These answers possessed a genuine beauty. They had the virtue of embracing the awe without dispelling it. But they never reached the actual source. They merely named the phenomenon without ever truly touching it. The true source is far stranger, and in many ways much more unsettling than any myth could ever manage to be. Imagine holding a single grain of sand in the palm of your hand. Just one grain, tiny, mundane, entirely forgettable. Now imagine that hidden inside this grain is a latent tension, a dammed-up reservoir of energy that, if fully released, could power an entire city for months on end. This tension is not chemical. It is not like burning coal or wood. It is far more fundamental. It is woven into the very fabric of what matter actually is. It exists because mass itself is simply a highly compressed form of energy. Because when the universe created particles with mass, it simultaneously forged an immeasurable reservoir of potential power that can be tapped when those particles combine in specific ways or split apart in others. This was the profound realization that Albert Einstein formalized at the dawn of the 20th century, encapsulated in an equation that takes up only a single line but completely reorganized humanity's understanding of the nature of reality. The relationship between energy and mass is not merely a convenient formula for mathematical calculations. It is a profound ontological statement. It declares that matter and energy are the exact same thing expressed in different forms, that the universe does not possess two separate ingredients, one static and one dynamic, but rather a single fundamental ingredient that can assume various distinct states, and that when matter undergoes transformation, when atoms fuse together or atomic nuclei split apart, a portion of this shared ingredient escapes in the form of radiant energy, of heat, of light. Einstein arrived at this conclusion not through a spectacular laboratory experiment, but through a long, deep meditation on the internal inconsistencies plaguing the physics of his era. He realized that the laws describing classical mechanics and the laws describing the behavior of light could not be entirely compatible as they were currently written. One of them had to yield, and by honestly following this tension, by refusing to accept the contradiction as inevitable, he was led to a vision of the cosmos where time and space are not absolute, where the speed of light is the fundamental limit for the transmission of information, and where mass and energy are simply two faces of the exact same phenomenon. The universe he described was not the universe he believed he had been born into. It was a place far more fluid, vastly more interconnected, and much more frightening in its absolute coherence. However, the question regarding the source of stellar energy was not answered by Einstein alone. Even after understanding that mass could be converted into energy, the specific mystery remained as to how the sun managed to burn for so long without exhausting all its fuel in just a few million years, which would have been completely incompatible with the geological and biological evidence pointing to a much older Earth. It was Hans Bethe who, in the decades that followed, accurately described the mechanism by which the sun and other stars convert hydrogen into helium through nuclear fusion, releasing a minuscule fraction of their mass as radiant energy in the process. Bethe worked with calm precision and methodical care. He was not a man given to dramatic proclamations. He was a physicist who tackled difficult problems with an almost artisanal patience. By meticulously mapping the chains of nuclear reactions occurring within stellar interiors, he demonstrated that the sun is essentially a gravitationally confined fusion reactor, where the pressure generated by the weight of a mass equivalent to 330,000 Earths creates core conditions of temperature and density so extreme that hydrogen nuclei overcome their mutual electrical repulsion and fuse together. And when 4 hydrogen nuclei combine to form a single helium nucleus, the final product weighs slightly less than the original ingredients. This difference, though minuscule in absolute terms, is released as pure energy. It is the very light that warms your skin on a summer afternoon. It is the heat that has kept the oceans liquid for billions of years. It is the radiation that, at a specific moment in Earth's history, energized the molecules that eventually learned how to copy themselves. The law governing this process has a name that sounds highly technical, but actually conceals something deeply poetic. It is the law of conservation of energy. It states that the total energy of an isolated system remains perfectly constant. That energy can neither be created out of nothing nor entirely destroyed. It merely changes its form. The heat radiating from a campfire previously existed as chemical energy locked within the molecular bonds of the wood, and before that as solar energy absorbed by the tree during decades of photosynthesis, and before that as nuclear energy deep within the sun's core, and before all of that as potential energy contained within the original distribution of matter that the universe possessed immediately after its birth. Tracing this chain of events backward is a dizzying experience. Every single transformation points to an earlier one. Every source reveals an even deeper source. This continues until you reach the point where the tracking fails, where the physics we understand loses its grip, and the mathematical tools that work so beautifully at all other scales begin to break down and diverge. The universe had a beginning, or at the very least an initial state so incredibly dense and hot that anything that might have come before is inaccessible by definition. And the energy that exists today is the exact same energy that existed in that initial moment, redistributed over billions of years through billions of different processes, but never created, never destroyed, only ever transformed. There is another law that works silently alongside the conservation of energy, and it is, in a certain sense, far more unsettling. It is the second law of thermodynamics. If the conservation of energy guarantees that nothing is ever truly lost, the second law ensures that not everything can ever be recovered. It dictates that in any real transformation, in any process that occurs spontaneously within the universe, the total disorder of the system always increases. That energy redistributes itself into forms that are progressively less concentrated, less usable, and less capable of performing useful work. Picture an ice cube dropped into a glass of warm water. The cold does not stay trapped in the ice, and the heat does not remain confined to the water. They mix together, the temperature equalizes, and once that equilibrium is reached, you cannot simply sit back and expect the ice cube to spontaneously reform inside the glass. The information regarding where the cold used to be has been diluted into the random, chaotic agitation of billions of molecules. The process moved in one specific direction, and it does not reverse. This is entropy in action. It is not a loss of total energy, but rather a loss of structure, of difference, of usable potential. The universe is constantly marching in this exact direction, always. The stars shine because there is a steep gradient, a massive difference between the extreme temperature of the solar core and the freezing temperature of the surrounding space. This gradient was established during the initial conditions of the cosmos, and as time marches on, as stars burn through their fuel and radiate it out into the void, this gradient steadily diminishes. The difference between hot and cold, between dense and diffuse, between structured and random, is slowly being consumed away. Rudolf Clausius, the 19th century German physicist who mathematically formulated this concept, deliberately chose the word entropy from the Greek word for transformation. He understood that he was naming something fundamental about the arrow of time, about why natural processes have a preferred unidirectional flow. James Clerk Maxwell, a contemporary of his, was so deeply disturbed by this idea that he invented a thought experiment to try and escape its implications. He imagined a microscopic demon capable of opening and closing a tiny door between two gas compartments, selectively allowing molecules to pass, thereby spontaneously creating a temperature difference without performing any apparent work. It seemed like a clever loophole, but decades later Leo Szilard and subsequently Charles Bennett demonstrated that the very act of the demon measuring and remembering the speed of the molecules carries an information cost that, when properly accounted for, perfectly preserves the second law. There is no escape. The universe makes no exceptions for imaginary demons. The reason this matters so much for the story of cosmic energy is that the universe, at the moment of its birth, was in a surprisingly low entropy state. Not because it was simple, but because the matter was distributed in a highly specific way that contained an immeasurable amount of potential difference. The microscopic quantum fluctuations of that initial state generated tiny irregularities in the distribution of matter, and those irregularities, under the relentless pull of gravity, acted as the trigger for absolutely everything that would follow. Gravity, the weakest of the fundamental forces in terms of intensity between individual particles, is the force that completely dominates on grand scales precisely because it is always attractive and because its effects accumulate with mass. Wherever there was a region slightly denser than its surroundings, gravity pulled more matter toward that region, making it even denser, which in turn pulled in even more matter, in a self-reinforcing cycle that lasted for hundreds of millions of years until the concentration was high enough to ignite nuclear fusion. The star turned on. This process is essentially an imbalance that generates structure, and this is exactly what seems paradoxical at first glance, but is actually the key to understanding why the cosmos has the shape it does. The second law of thermodynamics dictates that global disorder must increase, and it is absolutely right. But locally, temporarily, in specific pockets of the universe, energy flowing toward equilibrium can produce, along its path, islands of extraordinary organization. The heat escaping from the solar core toward the cold of space does exactly this as it crosses the sun's photosphere, traverses the 93 million miles of vacuum separating it from Earth, warms the oceans, drives the atmosphere, powers the water cycle, and fuels photosynthesis. Every single step toward final equilibrium generates along that journey an absurd amount of intermediate complexity. The physicist Erich Schneider and the biologist Dorian Sagan developed the idea that life itself is a direct expression of this dynamic. Not an exception to the laws of thermodynamics, but a highly sophisticated implementation of them. They described structures that capture energy from a low-entropy source, perform work with it, and then return it to the environment as dissipated heat. Plants absorb highly organized sunlight and emit diffuse heat. Animals consume complex chemical structures and excrete heat and simple compounds. Entire human civilizations burn through energy reserves accumulated over geological eras and dissipate them in mere decades. All of this is moving in the direction of equilibrium. All of this is in perfect compliance with the second law. And yet, all of this simultaneously produces along the way an elaboration of structure that simple, random mixing could never possibly generate. This is precisely why the universe is not just a homogeneous soup of particles sitting in perfect thermal equilibrium. It is because it is currently halfway through the journey. It is in transit between the initial low entropy state and the final maximum entropy state that physics refers to as heat death. And within this transit, which lasts for trillions of years, there is a brief window. A window in which stars, planets, atmospheres, oceans, and organic molecules exist, and for a cosmically fleeting instant, beings capable of perceiving and asking questions. Now, picture a single cloud of gas tucked away in some random corner of a young galaxy. It is cold, diffuse, composed primarily of hydrogen with trace amounts of helium and an ultrafine dust of heavier elements forged by stars that have long since died. There is nothing visually impressive about it. There is no brilliant glow, no dramatic flare. But there is an imbalance, a region just slightly denser than its immediate surroundings. Gravity begins to do its work. The cloud starts to collapse in on itself very slowly over the course of hundreds of thousands of years. As it collapses, it heats up. The pressure at the center steadily increases. Collisions between particles become more frequent and far more energetic. And when the imbalance between thermal pressure and gravity reaches the critical tipping point, when the temperature in the core crosses the threshold where the strong nuclear force begins to overpower electromagnetic repulsion, fusion ignites. A star is born. This is happening right here, right now, in this very galaxy. In other distant galaxies, in clouds that will never be seen by human eyes and that will transform into stars long after our own sun has burned out. It is a local mechanism repeated across different scales and contexts, in eras separated by intervals that have no name in human experience. And the question that hangs in the air, which does not demand an immediate answer, but plants a seed deep within your attention, is this. What happens when this mechanism repeats itself millions of times over billions of years across billions of galaxies, with each cycle leaving behind a legacy of heavier elements that will go on to fuel all subsequent cycles? When a star is born within a molecular cloud, it is never born alone. This is perhaps the most quietly revolutionary fact in all of observational cosmology. The universe does not manufacture stars individually, like a patient artisan crafting each piece one by one. It creates them in massive bursts, in sweeping waves, in episodes of collective creation that can last for tens of millions of years, and which, when viewed from far enough away, appear to bloom all at once, like spores released simultaneously by the same seismic tremor. What we call star formation is, in reality, a cascading event, and a cascade inherently possesses structure. The first of these structures that becomes visible when we look beyond the individual mechanism is the filament. The massive molecular clouds of the universe are not spheres. They are not clouds in the meteorological sense of the word, and they are not homogeneous blobs of gas just waiting patiently to collapse. They are woven. Observations at sub-millimeter wavelengths, particularly those conducted by the Herschel Space Observatory in the early years of the second decade of this century, revealed that virtually every molecular cloud of significant size is organized into a network of gas threads, dense along their central axes and progressively fainter toward the edges. These filaments have surprisingly consistent thicknesses, hovering around 1/10 of a parsec, a regularity that immediately suggests they are not formed by random accident, but by underlying physics. Magnetic compression, supersonic turbulence dissipating into shock waves, and gravity acting along the axis of least resistance all seem to conspire to create not a random texture, but a recurring geometry. And along these filaments, at the exact nodes where they intersect and where the density reaches its local peaks, the prestellar cores form. Stars are born at the junctions of the web. This profoundly shifts the way we think about how matter organizes itself on scales larger than a single cloud. If a cloud is essentially a filament, and those filaments are connected to even larger structures, then a clear hierarchy exists, and hierarchies carry deep consequences. A star born within a filament is not isolated. It is surrounded by other cores in various stages of collapse, by protostars that have already ignited their fusion, and by the remnants of stars that have already died and left the local gas enriched with heavy elements forged in their cores. Each generation of stars prepares the environment for the next, not out of conscious intention, but purely through physics. Stellar winds, supernova explosions, and the ionizing radiation from massive stars all compress the surrounding gas, trigger new episodes of collapse, and propagate the wave of star formation along the filament like a tremor travelling through a web. There is propagation. There is a sequence in time. There is something that can only accurately be described as inheritance. And when we zoom out from the scale of a single cloud to the scale of an entire galaxy, the underlying structure does not vanish. It amplifies. A spiral galaxy like the Milky Way, when viewed from above in radio or infrared wavelengths, reveals its arms not as regions of higher stellar density, but as regions of higher cold gas density and active star formation. The spiral arms are not material structures in the way a river is material. Stars continuously enter and exit them along their orbital paths. What the arm actually represents is a density wave, a perturbation that travels through the galactic disk more slowly than the stars themselves, so that the gas encountering the arm gets compressed, cools down much faster, reaches the threshold for gravitational collapse, and produces stars, which then travel past the arm and continue on their orbits, aging and dying while the arm itself persists as a lasting pattern. Lin and Xu formulated this concept of spiral density wave theory back in the 1960s, and it completely transformed our understanding of galaxies. What appeared to be a static structure was, in reality, a dynamic pattern, sustained by the physics of waves propagating through a disk of gas and stars undergoing differential rotation. Differential rotation is an ingredient that deserves particular attention here. Unlike a rigid body that spins as if it were completely solid, most spiral galaxies rotate in such a way that their inner regions complete their orbits much faster than their outer regions. This difference in angular velocity acts upon any elongated structure of gas like a massive stretching machine. Clouds that originally might have had any random orientation are progressively twisted and stretched in the direction of orbital motion, aligning themselves along arcs that, when viewed from a great distance, look exactly like spiral arms. The spiral geometry is not painted onto the universe. It naturally emerges from the combination of the density perturbation that organizes the gas and the differential rotation that stretches it out. It is a shape produced entirely by dynamics, not by any deliberate design, and this shape in turn directly dictates where stars are allowed to be born. Regions where the arms of a galaxy intersect, where the geometry creates confluences of highly compressed gas, act as preferred stellar nurseries. The distribution of star-forming regions within a galaxy is therefore directly mapped out by the rotational geometry of the disk. Form and process mutually determine one another. The galaxy has no central planning committee. None of its individual parts possesses a vision of the whole, and yet the whole undeniably has a pattern. It has symmetry. It has arms that persist for hundreds of millions of years, while the individual stars illuminating them die and are continually replaced. It is an organization that completely lacks an organizer. William Herschel, toward the end of the 18th century, attempted to map the Milky Way by counting stars in various different directions across the sky. His method was inherently limited, and the light-absorbing interstellar dust deceived him. But his underlying impulse was absolutely correct. There was a grand structure waiting to be discovered. Henrietta Swan Leavitt, in the early 20th century, made the breakthrough discovery that Cepheid variable stars had a pulsation period directly related to their intrinsic luminosity. This brilliant finding transformed Cepheids into reliable cosmic yardsticks. Edwin Hubble subsequently used them to measure the distances to spiral nebulae, and discovered that they were located far beyond the boundaries of the Milky Way, proving they were galaxies in their own right, islands of hundreds of billions of stars separated from us by unimaginable voids. In a single series of observations, the known universe expanded by a factor of many millions. What had previously appeared to be mere mist within our own galaxy was, in truth, an entire separate cosmos, and there were countless others just like it. Vera Rubin and Kent Ford, while measuring the rotation curves of spiral galaxies in the 1970s, stumbled upon something that simply should not have been there, according to standard models. According to basic Newtonian physics, stars at the extreme outer edges of a galaxy should orbit much more slowly than those near the interior, in the exact same way that the outer planets of our solar system orbit more slowly than the inner ones. But the rotation curves of these galaxies were completely flat. The stars at the very edges were moving just as fast as those close to the centre. For this to be physically possible, there had to be vastly more mass present than what was actually visible. A type of mass that did not emit, absorb or reflect any light, dark matter. And the distribution of this invisible matter, as subsequent models revealed, is not concentrated in the galactic disk where the stars reside. Instead, it forms a massive spherical halo that envelops the entire visible galaxy, extending far beyond the luminous disk. The galaxy we actually see, with its elegant spiral arms and bright star-forming regions, is merely the glowing core of a much larger and completely invisible structure. This profound discovery directly connected what happens inside a single galaxy with what happens in the vast spaces between galaxies. Because if galaxies possess halos of dark matter, then neighbouring galaxies have halos that touch, overlap, and exert gravitational forces upon one another through invisible layers long before any visible contact occurs. Furthermore, galaxies are not distributed randomly throughout the universe. They cluster together. There are massive clusters of dozens or hundreds of gravitationally bound galaxies, superclusters containing hundreds of thousands, and beyond all of that lies the large-scale structure of the universe that astronomers refer to as the cosmic web. The cosmic web is the absolute largest structure in existence. It consists of gigantic filaments of matter, geometrically analogous to the filaments found in molecular clouds, but on scales hundreds of millions of times larger, separated by immense voids that can span hundreds of millions of light years in diameter. At the dense nodes where these filaments intersect reside the very largest clusters of galaxies. Along the length of the filaments, galaxies are distributed like pearls strung on a necklace. Within the voids, the density of matter drops to almost absolute zero, and this intricate pattern, this cosmological scale geometry, was never consciously planned. It naturally emerged from the tiny density fluctuations of the primordial universe, amplified by gravity over billions of years, channeled by the distribution of dark matter which acted as an invisible scaffolding, and ultimately defined the pathways along which ordinary gas flowed, cooled, and eventually coalesced to form galaxies. The large-scale maps of the universe, painstakingly constructed over the last few decades by massive surveys like the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey, have made this web visible in a way that deeply impresses even veteran cosmologists. The universe undeniably has texture. It possesses filaments, dense nodes, bubble-like surfaces, and vast empty voids. And this observed texture, when carefully compared with complex computer simulations modelling the evolution of the universe from its primordial fluctuations, matches up in a way that goes far beyond mere coincidence. The standard cosmological model, complete with all its dark matter and dark energy, perfectly reproduces the cosmic web. The grand structure we observe in the real universe is exactly the structure that fundamental physics predicts. However, there is a crucial nuance in this correspondence that deserves to be stated with great care. The physics that primarily produces the cosmic web is the physics of dark matter. Ordinary matter, the gas, the stars, the planets, the carbon, the oxygen, absolutely everything that can be touched and seen, represents only a tiny fraction of the total material content of the universe. The vast majority of matter is dark, invisible, and does not interact in any way that our instruments can directly register. And dark matter, precisely because it does not interact with light, cannot dissipate energy in the highly efficient way that common gas does. It falls into gravitational wells and forms large halos, but it cannot collapse down into even smaller structures. It does not form stars, it does not form planets, it does not form anything that we can possibly see. What allows ordinary matter to do something completely different, to sink much deeper into the gravitational wells created by dark matter, to cool down, to fragment into distinct clouds, filaments, and dense cores, is precisely its unique ability to radiate energy outward and shed the heat generated by gravitational pressure. This cooling process, this specific mechanism by which common gas separates its behavior from dark matter and concentrates into much denser structures, is exactly what makes everything we see possible. And within these highly condensed structures, the gas possesses chemical composition, magnetic fields, supersonic turbulence, an entire universe of complex physics that dark matter completely lacks. The cosmic web determines the general locations where galaxies form, but what actually happens inside a given galaxy, the rich complexity of its molecular filaments, the precise geometry of its spiral arms, the cascading waves of star formation propagating from cloud to cloud across generations, all of this depends on something much more specific. It relies on a physics that goes far beyond simple gravity, involving temperature, chemical composition, and magnetic fields, and it would become almost entirely unrecognizable if the universe had remained populated solely by the simplest elements present at its very beginning. The great amplifier that transforms the cosmos from a dreary expanse of diffuse gas into a brilliant theatre of light and complex structure is not a gigantic object, nor an exotic fundamental force, nor something easily spotted even through the world's most powerful telescopes. It is an element small enough to fit inside a single atom, one that has existed since the very first minutes after the dawn of everything, and which for hundreds of millions of years simply drifted through space doing almost nothing at all. It is carbon, and following closely behind it in a grand cascade are oxygen, nitrogen, silicon and iron, all of them forged deep inside the hearts of stars that lived and died long before our sun ever existed. All of them scattered across the void by violent explosions that last only a few brief weeks, yet release more energy than our sun will radiate over its entire multi-billion-year lifespan. It is this specific chemistry, this vital presence of heavy elements within the interstellar gas, that changes absolutely everything. It transforms the universe from a place where things form slowly and with very little variety into a vibrant realm where solid worlds emerge, complex molecules assemble, surfaces exist where liquid water can pool, and eventually living organisms arise that can look up at the night sky and wonder exactly where they came from. The epic story of carbon in the cosmos begins deep inside medium and high-mass stars, those that burn brightly for tens or hundreds of millions of years before ultimately dying in catastrophic collapse and explosion. For the vast majority of their lives, these stars steadily fuse hydrogen into helium in their cores, but when the hydrogen fuel is finally exhausted at the center, the star contracts, heats up dramatically, and begins fusing helium into carbon through a mechanism physicists call the triple alpha process, because it requires the simultaneous combination of 3 helium nuclei. This specific process is extraordinarily sensitive to exact conditions of temperature and pressure. The result is that carbon slowly accumulates in the star's core over millions of years, completely silently, while the outer surface of the star expands and cools, swelling into a red giant large enough to swallow the entire orbits of inner planets. When this star eventually violently expels its outer layers, either in a spectacular supernova explosion or a gentler planetary nebula ejection, the carbon is cast out right alongside the helium nitrogen, oxygen, and everything else synthesized during the star's active life. This newly forged material mixes with the surrounding interstellar gas, chemically enriching it. And it is precisely this chemical enrichment that allows the very next generation of stars to be fundamentally different from the ones that came before. The difference that heavy elements make in the behavior of interstellar gas is absolutely enormous, and it operates primarily through a mechanism astronomers refer to as metal cooling. When a gas cloud is composed purely of hydrogen and helium, it can only cool down in relatively inefficient ways, mostly through the emission of radiation when free electrons and protons recombine. This process does work, but it is painfully slow, and a gas that cools slowly takes much longer to condense, takes much longer to reach the extreme densities required to ignite stars, and tends to form incredibly massive stars when it finally does collapse, simply because the internal thermal pressure remains high throughout the process. But when the gas contains carbon, oxygen, silicon, and other heavy elements, it suddenly has vastly more avenues available to shed heat. Molecules like carbon monoxide can efficiently radiate away rotational energy at radio wavelengths. Tiny grains of interstellar dust composed of silicates and graphite readily absorb harsh ultraviolet light and re-emit that energy as gentle thermal infrared. The ultimate result is that molecular clouds enriched with metals can cool down to temperatures of just 10 kelvins above absolute zero, temperatures far colder than any natural place most people could possibly imagine on Earth. And at those freezing temperatures, the internal pressure of the gas drops so low that relatively small fragments of the cloud can easily collapse under their own gravity, forming much lower mass stars far more similar to our Sun, stars that burn much longer, and in many cases stars surrounded by protoplanetary disks that will eventually mature into full systems of orbiting planets. This grand cascade of cooling, condensation, and star formation propagates itself through galaxies in ways that directly create the visible structures we observe today. When a highly massive star forms within a molecular cloud, it emits an absolutely enormous amount of ultraviolet radiation that fiercely ionizes the surrounding gas, creating what astronomers call an H2 region, a glowing bubble of ionized gas that shines bright red due to the hydrogen H-alpha emission line. This exact same radiation heats and compresses the adjacent molecular cloud, frequently triggering the collapse of brand new fragments and the birth of new stars right along the edges of the ionized region. This process, known as triggered star formation, means that the birth of stars propagates through a molecular cloud like a slow-moving wave, rolling forward over millions of years, from one stellar generation to the next. The spiral arms of spiral galaxies clearly mark the regions where this wave of star formation is currently most active, where the molecular clouds are being heavily compressed by the density waves rolling through the galactic disk, and where the brilliant blue light of young, massive stars starkly contrasts with the softer red glow of much older stars in the intermediate regions. Iron deserves a very special mention in this narrative, because it simultaneously represents both the absolute pinnacle and the hard limit of stellar nucleosynthesis. Deep inside a massive star that is rapidly approaching the end of its life, there exists a series of concentric shells of nuclear fusion, with each layer burning a progressively heavier element than the one outside it. Hydrogen in the outermost shell, helium just below that, then carbon, followed by neon, oxygen, silicon, and finally, right at the very centre, iron. Iron occupies a highly singular position on the periodic table from an energetic standpoint. It possesses the most stable atomic nucleus in existence. Fusing iron does not release energy, it actively consumes it. And when the iron core of a massive star reaches a critical mass equivalent to about 1.4 times the mass of our Sun, it catastrophically collapses in a fraction of a second, triggering the colossal supernova explosion that violently disperses all the heavy elements accumulated during the star's life out into the interstellar medium. This is exactly why iron is so incredibly abundant in the universe. far more abundant than it would be if stars could somehow manage to continue fusing elements beyond it, and this is precisely why the iron sitting inside the red blood cells of every living creature on Earth, that vital iron responsible for transporting oxygen through veins and arteries, was originally forged in the core of a star that died long before our sun even formed, and it only arrived here because that ancient star violently exploded. The visible manifestations of this ongoing process of chemical enrichment and star formation produce some of the most famous and iconic images in all of modern astronomy, but merely knowing their names does absolutely nothing to diminish the profound depth of what they actually represent. Emission nebulae, such as the Great Orion Nebula, are brilliant H2 regions where newly born stars fiercely illuminate the surrounding gas. The Orion Nebula sits approximately 1,300 light-years away, and deep inside it, right at this very moment, the formation of entirely new solar systems is actively taking place. When you observe this nebula through a telescope, even a relatively small one, and perceive that fuzzy patch of greenish and pinkish light, you are actively witnessing the process of world-building happening in real time, with the only minor caveat being that the light reaching your eyes actually departed from there 1,300 years ago, meaning that what you are seeing is a relatively recent past in cosmic terms, yet still profoundly distant in human terms. Planetary nebulae represent a completely different stage of the exact same stellar story, capturing the precise moment when a medium-mass star, much like our Sun, violently expels its outer layers as it transitions into a white dwarf. The term planetary nebula is merely a historical artifact, coined by the astronomer William Herschel in the late 18th century, simply because these structures, when viewed through the small telescopes of his day, possessed a rounded appearance vaguely reminiscent of a planetary disk. But they have absolutely nothing whatsoever to do with actual planets. They are expanding shells of gas racing outward at speeds of tens of kilometers per second around a dying star that is rapidly heating up as it sheds its outer envelopes. The central star, which will eventually cool into a white dwarf, emits such intense ultraviolet radiation that it fiercely ionizes the gas in the expanding shell, causing it to glow brilliantly. The vivid colours of these nebulae directly reflect their chemical composition. Doubly ionized oxygen emits in vibrant greens and blue-greens, ionized hydrogen emits in the deep red of the H-alpha line, and ionized nitrogen emits in a slightly different shade of red. The striking geometric beauty found in many planetary nebulae, with their perfect rings, their dramatic bipolar jets, and their intricate internal filamentary structures, is still not completely understood and remains a subject of highly active research. The complex geometry directly reflects the underlying physics of the stellar wind, the tangled magnetic fields, the rotation of the dying star, and subtle interactions with binary companions that are often not even directly visible, but leave their unmistakable signature imprinted on the shape of the nebula. Supernova remnants are even more dramatically violent structures, consisting of massive bubbles of shocked gas expanding outward at mind-boggling speeds of thousands of kilometers per second, creating immense shock waves that heat the surrounding interstellar gas to tens of millions of kelvins and cause it to emit brightly in X-rays. The Crab Nebula, which Western astronomers first recognized by cross-referencing historical Chinese and Arabic records describing a guest star that became so brilliantly bright during the day of its explosion that it was visible to the naked eye for weeks in the year 1054, is today an expanding nebula roughly 11 light-years in diameter. Right at its centre pulses a rapidly spinning pulsar, the ultra-dense collapsed remnant of the original stellar core, rotating 30 times every single second and emitting tight beams of radiation with such metronomic regularity that it completely bewildered astronomers when pulsars were first discovered in the 1960s, leading some scientists to joke, before they fully understood what they were looking at, that they might actually be detecting signals from extraterrestrial intelligence. The profound realization that these grand cosmic processes have direct, tangible consequences for the immediate, everyday experience of any breathing person is something that takes a considerable amount of time to truly sink in with its full force. The oxygen in every single breath you take was largely produced deep inside the hearts of stars. Although a highly significant fraction of Earth's atmospheric oxygen was released biologically, through the photosynthesis of ancient cyanobacteria and modern plants over billions of years, the iron sitting inside the enzymes that catalyze vital biochemical reactions within your cells, the calcium strengthening your bones, the phosphorus forming the backbone of your DNA, the magnesium at the center of every chlorophyll molecule, all of these essential elements were originally synthesized in generations of ancient stars that lived and died long before our sun was even a glimmer. The Earth itself, the solid rocky ground where all of this takes place, is made largely of silicates, complex combinations of silicon and oxygen that only form under the extreme conditions found either deep inside stars or within the violent shockwaves of supernovae. The silicon present in every single grain of sand on every beach across the planet has endured conditions of temperature and pressure that exist nowhere else except within stellar interiors. There is a distinct, apparent equilibrium in the observable cosmos today, a delicate balance that has expressed itself over billions of years of continuous cycles of star formation, chemical enrichment, galaxy assembly, and the evolution of large-scale structures. The existing galaxies appear remarkably stable when viewed on human timescales. Our Milky Way completes one full rotation roughly every 250 million years, and over the course of billions of years, it has successfully completed dozens of these grand rotations without ever flying apart. The overall rate of star formation across the universe actually reached its absolute peak about 10 billion years ago, and has been slowly declining ever since, meaning that today the universe is forming stars at a mere 1/10 the rate it did during its most active, vibrant period. Galaxies are undeniably aging, their vital reserves of cold gas are steadily depleting, and their stellar populations are progressively becoming redder and much older. But this aging process is incredibly gradual, almost entirely imperceptible on any human or even historical timescale. However, this apparent equilibrium is built entirely upon a series of underlying processes that are intrinsically unstable, relying heavily on precise coincidences of scale and physical constants that have no obvious reason to be exactly the way they are. The specific density of dark energy, which is currently causing the universe to expand at an accelerating rate, did not absolutely have to possess the exact value it does. If it were even slightly larger, the universe would have expanded so furiously fast that galaxies could never have formed. If it were slightly smaller, the universe might have already collapsed back in on itself. The delicate balance between the gravity that pulls things together and the expansion that pushes them apart, the balance between the cooling that allows condensation and the heating that prevents excessive fragmentation, the balance between the rate of new star formation and the rate of gas consumption. All of this is fine-tuned in a way that successfully produced a universe where galaxies, stars, planets, and everything else can actually exist. But this equilibrium is by no means eternal. There are silent perturbations steadily accumulating, massive collisions slowly approaching over billion-year scales, and underlying processes that are continually transforming cosmic structures in ways that only become visible when we observe the universe across timescales far longer than any human civilization has ever existed to directly witness. The cosmos in perfect equilibrium is merely a frozen snapshot of one particular moment in a vastly longer story, and deep beneath the apparent stability of the galaxies and stars, there are relentless forces continuing to shape the ultimate destiny of everything that exists. These silently accumulating perturbations possess a highly peculiar nature. They never announce their impending arrival. The cosmos does not suddenly change colour, nor does it emit any loud, audible signal when one galaxy begins to drift dangerously close to another, when a supermassive black hole starts to violently awaken after long epochs of deep dormancy, or when a massive star finally crosses the critical internal threshold beyond which nuclear fusion can no longer support the crushing weight of its own outer layers. All of these monumental events unfold in such a way that, to any observer confined within the narrow limits of a human timescale, the universe appears completely and utterly static. But the deep time of the cosmos possesses a level of patience that goes far beyond our intuitive capacity to comprehend. And once that critical threshold is finally crossed, the resulting transformation is absolute and total. Instability within the cosmos looks absolutely nothing like the sudden instability we're accustomed to in our everyday lives. It is not something that just happens abruptly without any prior warning. It is something that slowly prepares itself over hundreds of millions of years, steadily accumulating the necessary conditions, much like water, building up immense pressure behind a massive dam. And when it finally does manifest, it does so with an explosive energy that has absolutely no parallel anywhere else in physical experience. The universe is full of critical thresholds, and every single one of them represents a distinct point beyond which the previously ongoing processes can simply no longer continue in the same manner. From that point forward, everything fundamentally changes its state, its physical form, and its entire scale of operation. To truly understand what happens when one of these thresholds is crossed, one must first remember everything that was carefully built beforehand. In the earlier stages of this journey, we explored how the primordial hydrogen slowly condensed, how the very first stars ignited their nuclear cores, how galaxies gradually formed and grew over billions of years of gravitational evolution, and how the delicate balance between opposing forces allowed highly complex structures to exist. This entire grand process was much like constructing a cosmic architecture of extraordinary complexity, building it up layer by careful layer, and highly complex architectures inherently possess hidden points of vulnerability that only fully reveal themselves when the accumulated tension finally reaches its absolute breaking point. The very first of these critical thresholds that deserves our close attention occurs entirely internally within stars. A star much like our Sun exists in a state of stable equilibrium because the outward thermal pressure generated by hydrogen fusion in the core perfectly resists the immense inward gravitational pressure of the outer layers, desperately trying to collapse. This delicate equilibrium lasts for roughly 10 billion years, a number so vast that, when written out completely, it is difficult to even pronounce without losing all sense of scale. But the hydrogen fuel in the core is progressively depleted. As the core exhausts its primary fuel, it begins to contract, heats up dramatically, and eventually ignites the fusion of helium. The star responds to this internal shift by enormously expanding its outer layers, transforming itself into a bloated red giant. This represents the first intense mode of stellar operation. No longer the stable, long-lasting burn of hydrogen, but the accelerated, highly complex burning of increasingly heavier elements, in a process that generates multiple, concentric shells of simultaneous fusion, with each shell burning a completely different element and producing the necessary ash to serve as fuel for the next layer inward. For stars possessing many times the mass of our Sun, this internal process deepens drastically until the core is desperately trying to fuse iron. Iron represents the absolute end of the line for energy-producing nuclear fusion. Fusing nuclei lighter than iron releases vast amounts of energy, but attempting to fuse iron actively consumes energy. When the iron core of a truly massive star finally reaches its critical size, it catastrophically collapses in a fraction of a single second, and what immediately follows is one of the most unimaginably violent releases of energy that the entire universe can produce. A supernova is not merely the quiet death of a single star. It is an explosion so fierce that for days or weeks it can easily outshine the combined light of the entire host galaxy, flooding the surrounding space with devastating shockwaves, with ultra-high energy radiation, and with highly charged particles that will continue propagating through the interstellar medium for countless eras long after the initial event. The the physical remnants of these colossal explosions, the vast nebulae that slowly expand outward through space, are visible to us today as structures of extraordinary beauty and intricate complexity, woven entirely from gas and dust, heavily enriched with all the heavy elements that the star painstakingly synthesized throughout its entire life and then violently dispersed in its death throes. Humanity has slowly learned to carefully observe these awe-inspiring phenomena with immense patience and with instruments of truly extraordinary precision. Space telescopes situated high above the blurring atmosphere, massive radio telescopes that capture emissions at wavelengths the human eye could never possibly see, and highly sensitive gamma ray detectors that register the most energetic photons in the universe. All of these incredible instruments function as direct extensions of human senses, specifically designed to reach out and touch scales that remain completely outside our direct, everyday experience. When a distant supernova violently explodes in a faraway galaxy, astronomers sitting in their control rooms carefully watch the spectrum of light arriving from that specific point in the sky change its shape over the course of days and weeks, revealing exactly which elements were dispersed, precisely measuring the expansion velocity of the shockwave and accurately calculating the original mass of the star that just died. The deeply dramatic phenomenon, occurring at mind-boggling distances of tens of millions of light-years away, is painstakingly reconstructed in vivid detail from the faint information that eventually reaches us in the form of visible light, radio waves, and X-rays. But supernovas, no matter how visually spectacular they might be, represent only one specific mode of intensity within the vast cosmic repertoire. There is an entirely different process that operates on even grander scales, and which was, for many decades, only indirectly inferred before finally being observed directly: the merging of entire galaxies. Two massive galaxies that gravitationally attract each other over billions of years, slowly drawing closer on trajectories that initially appear parallel, but which gravitational curvature gradually warps and deforms into a fatal inward spiral, eventually interpenetrate one another completely. And it is right here that the intense mode of the cosmos reveals one of its most surprising characteristics. During the messy merger of two galaxies, the individual stars almost never actually collide directly with one another, simply because the physical space between stars within any given galaxy is so unimaginably vast compared to the tiny physical size of the stars themselves. What actually collides is the gas, the interstellar medium, and the complex density waves propagating through the galactic disk. And these massive gas collisions severely compress the interstellar medium in certain specific regions, triggering intense starburst episodes of star formation of a sheer magnitude that simply never occurs in isolated, stable galaxies. Even while you peacefully rest right now somewhere out in the deep cosmos tens of millions of light years away from us, a massive galactic merger just like this is actively happening. Two giant spiral galaxies, each harboring hundreds of billions of individual stars, are currently interpenetrating in a slow, majestic gravitational ballet that will last for hundreds of millions of years. The massive gas clouds belonging to the two galaxies are violently colliding at speeds of hundreds of kilometers per second, heavily compressing, rapidly heating up, and fragmenting into much smaller clouds that subsequently collapse under their own intense gravity. Where there previously existed only a moderate, steady rate of stellar birth, there is now a blinding explosion of star formation that produces in just a few short million years as many new stars as would normally be formed over billions. The most massive stars born during these intense starbursts will live for only a few brief million years before violently exploding as supernovae, rapidly flooding the surrounding interstellar medium with vast amounts of energy and newly forged heavy elements. The resulting merged galaxy is simultaneously something entirely new being born, and something ancient dying, something creatively building, and something violently destroying. Astronomers carefully measure this ongoing process by photographing pairs of interacting galaxies caught in various different stages of interaction and then meticulously reconstructing the history of the encounter using highly advanced computational models. Modern computer simulations of galactic mergers run continuously on massive supercomputers for weeks on end, tracking the complex gravitational movements of billions of individual particles representing stars, gas, and dark matter across hundreds of millions of years of simulated time. The final results of these complex simulations perfectly agree with exactly what our telescopes observe in real galaxies currently caught in various stages of merging, allowing scientists to confidently construct a highly coherent narrative of exactly how these massive cosmic encounters develop from their very beginning to their final end. Our own home galaxy, the Milky Way, still bears the distinct scars of past mergers clearly visible in long stellar streams that snake gracefully around the galactic disk, serving as silent, enduring testimonials to smaller satellite galaxies that were completely absorbed over the course of billions of years. There exists an even more extreme phenomenon than the merging of entire galaxies, and it is directly associated with the supermassive black holes that quietly inhabit the very centers of almost all large galaxies. For the vast majority of a galaxy's long existence, the central black hole remains in a relatively quiet, dormant state. It grows very slowly as stray stars and random gas gradually fall inward toward it, but it is simply not processing nearly enough material to produce any truly dramatic electromagnetic emissions. But the moment a major galactic merger occurs, or when other mechanisms successfully funnel massive quantities of gas directly toward the galactic center, the black hole suddenly snaps into a highly active mode. The gas falling inward toward the black hole does not just drop straight in. Instead, it forms a swirling accretion disk, a flat, rapidly spinning structure that heats up due to intense friction and radiation to absolutely extreme temperatures. This glowing disk shines with an intensity that can easily outshine, by many vast orders of magnitude, the combined light of all the hundreds of billions of regular stars making up the host galaxy. These active galactic nuclei, known in their most powerful and extreme versions as quasars, remained a profound, unsolved mystery for the field of astronomy for many decades. When the very first quasars were initially discovered, they appeared to be ordinary stars because they looked like point sources and were extraordinarily bright, but their light exhibited a massive redshift that firmly placed them at absolutely enormous cosmological distances. The sheer amount of energy required to make an object located at such vast distances appear so blindingly bright in our telescopes had absolutely no plausible explanation within the theoretical models existing at the time. It was only when the theoretical physics of black holes developed sufficiently that it finally became clear that the rapid accretion of mass by a supermassive black hole is the single most efficient process for converting mass into energy that the entire universe produces, making it even vastly more efficient than the nuclear fusion that powers regular stars. A surprisingly tiny fraction of the total mass falling inward toward a black hole is entirely sufficient to fully explain the staggering luminosity of the very brightest quasars. But the highly intense mode of quasars produces something even far more dramatic than just visible light. It produces massive relativistic jets. In many active galactic nuclei, the central black hole violently launches tight jets of superheated plasma straight outward along the exact rotation axis of the accretion disk, perfectly perpendicular to the plane of the disk, with velocities that closely approach the absolute speed of light. These powerful jets extend outward across distances that, in many cases, vastly exceed the physical size of the very galaxy that produced them, propagating for hundreds of thousands of light years out into deep intergalactic space before they finally slow down and dissipate, exactly where the high-energy jet slams into the thin gas of the intergalactic medium. It creates enormous radio structures that are clearly visible in large radio telescopes as giant, bright lobes flanking the central host galaxy. These massive structures persist for a very long time even after the central quasar itself has completely faded away, acting much like permanent scars left deeply etched into the fabric of space by a process of extraordinary intensity that has long since passed. Persistence is an absolutely crucial aspect of the most dramatic phenomena in the cosmos. They always leave behind physical marks that endure. A massive supernova that violently exploded 50,000 years ago is still clearly visible today as a rapidly expanding nebula. A colossal galactic merger that occurred billions of years in the past is still easily detectable in the faint stellar streams that continue to wrap around the resulting merged galaxy. A powerful quasar jet that was highly active billions of years ago can still be reliably inferred by the specific distribution of hot gas out in intergalactic space that it intensely heated and forcefully expelled. The cosmos operating in its intense mode does not merely transform the immediate present, it physically writes into the fabric of space massive structures that persist for vast periods of time that human language can barely even begin to name. The highly dynamic structures generated in this intense mode are simultaneously the direct consequences of deep past processes and the vital initial conditions required for all future processes. It is precisely here that something begins to become clearly evident, something that this particular part of the journey has only briefly pointed toward without yet fully developing. The most dramatic phenomena in the cosmos never happen in complete isolation. The supernova that heavily enriches the surrounding interstellar medium with heavy elements is absolutely not a separate, disconnected event from the formation of the very next generation of stars within that exact same medium. The powerful quasar that intensely heats the intergalactic gas is not entirely independent of the ongoing rate of star formation in the nearby surrounding galaxies, which it directly affects by fundamentally altering the physical conditions of the vast gas reservoir from which those galaxies continually feed. The massive galactic merger that triggers a violent starburst is not disconnected from the subsequent chemical enrichment that inevitably results from the rapid explosions of the highly massive stars that the starburst produces. The cosmos operating in its intense mode clearly reveals that absolutely everything is deeply interconnected in vast chains of causality that stretch across scales of space and time far beyond the limits of any single individual phenomenon. These vast chains of causality that stretch entirely across the cosmos are not mere philosophical abstractions. They manifest themselves directly in hard, concrete data, in careful observations that took many decades to properly gather and accurately interpret, and in distinct patterns that only finally became visible when humanity learned how to look out at the universe using wavelengths of light that the naked human eye could never possibly detect. And what all of this accumulated data reveals, in an increasingly unequivocal manner, is that the cosmos is absolutely not just a random collection of separate objects evolving quietly in parallel. It is a single, unified system. A system in the very deepest sense of the word. A highly complex network of continuous interactions where a fundamental change in any single component inevitably reverberates through all the others, where the deep past of every single part partially determines the future of all the rest, and where the rigid boundaries between seemingly individual phenomena completely dissolve the moment you zoom out far enough to finally see the entire, complete picture. The most fundamental partner within this vast web of relationships is one that very rarely appears in the spectacular, colourful images produced by our telescopes, precisely because it remains completely invisible at almost all the wavelengths of light we are currently capable of detecting. The interstellar and intergalactic medium, that incredibly vast reservoir of thin gas and fine dust that completely fills the empty spaces between individual stars and entire galaxies, acts as the silent intermediary through which almost all the crucial exchanges of energy and matter in the entire cosmos are processed. Stars are physically born when dense regions of this exact medium collapse inward under their own heavy gravity. Stars inevitably die by returning back to that very same medium all the heavy elements they painstakingly forged during their active lives. Powerful quasars intensely heat and heavily ionize this gas, temporarily rendering it completely incapable of collapsing to form any new stars. Massive galactic winds, strongly driven by the combined collective pressure of countless supernovae, and the intense radiation from hot young stars forcefully expel gas completely out of the galactic disk, pushing it into the halo and eventually out into the wider intergalactic medium. And this exact same gas, after slowly cooling down over hundreds of millions of years, can ultimately return, gently precipitating back down into the galaxy in long filaments that actively feed a brand new generation of stellar formation. This continuous cycle of violent expulsion and gentle reaccretion is by no means perfectly uniform. It actively pulses during periods of extremely high activity, when star formation is at its absolute peak and the resulting galactic winds are at their most powerful. Gas is expelled outward far more rapidly than it can possibly return. The galaxy essentially begins to starve itself of its own vital fuel. Consequently, the overall rate of star formation sharply drops. Without a sufficient number of massive stars left to sustain the powerful winds, the outward pressure that was forcefully expelling the gas significantly decreases. The expelled gas slowly cools down and eventually returns. The process of star formation then begins all over again. It is a classic cycle of negative feedback, a highly effective self-regulating mechanism that successfully prevents galaxies from rapidly consuming all of their available fuel in one single, massive burst, and which keeps them in a stable state of moderate, sustainable activity for vast periods of time that can easily extend across billions of years. The hard data that ultimately revealed this complex cycle came from multiple, highly convergent sources. Careful observations in ultraviolet light successfully detected the distinct spectroscopic signature of gas, simultaneously moving both inward toward galaxies and outward away from them, clearly revealing that this bidirectional flow is not a rare anomaly, but actually a nearly universal condition among galaxies that are still actively forming new stars. Massive computer simulations attempting to accurately reproduce the formation of galaxies over the course of cosmic history can only successfully reproduce the actual observed properties of these galaxies when they explicitly incorporate these exact cycles of expulsion and reaccretion. Without them included, the simulated galaxies convert their available gas into stars with a vastly higher efficiency than what is actually observed in reality, producing theoretical objects that simply do not exist anywhere in the real universe. The cycle, therefore, is not merely an elegant theoretical hypothesis. It is an absolute necessity strictly imposed by the observational data. But the single most dramatic feedback loop that the cosmos has ever produced is definitely not the one operating entirely inside individual galaxies. It is the one operating intimately between entire galaxies and their central supermassive black holes. This profound relationship was initially discovered in a highly indirect way, through an unexpected statistical correlation that completely bewildered astronomers when it was first identified. The total mass of the supermassive black hole sitting right at the centre of a galaxy, an incredibly dense object occupying an infinitesimally small physical volume compared to the vast host galaxy surrounding it, correlates with remarkably precise accuracy to the total mass of the stellar bulge enveloping it. Here are two objects of completely different physical natures, separated by massive scales of size differing by a factor of tens of billions, yet somehow growing in perfect synchrony over billions of years of deep cosmic history. This striking correlation absolutely demands a solid physical explanation, and the most convincing explanation that current theoretical models can offer is that the central black hole actively regulates both its own growth and the overall growth of the host galaxy through a powerful feedback mechanism. When the black hole is rapidly accreting mass, such as during its highly active quasar phase, the truly enormous amount of energy released intensely heats and forcefully expels the very gas that is simultaneously feeding both the growth of the black hole and the formation of new stars out in the galaxy. The rapid growth abruptly halts. The black hole settles down and cools. The surrounding gas slowly cools. The growth process then restarts on a much smaller, manageable scale. The entire system continually oscillates toward a stable equilibrium. and the ultimate result of this equilibrium reached completely independently across vastly different histories in entirely different galaxies all around the observable universe is always the exact same precise mathematical relationship between their respective masses. It is almost as if the cosmos had successfully discovered an elegant solution to the complex problem of how to properly distribute energy within a tightly coupled system, and that specific solution proved so incredibly robust that it naturally repeats itself everywhere. The apparent behaviour of this complex system changes dramatically depending entirely on the specific timescale on which you choose to observe it. Over mere decades, roughly the active lifespan of an individual human astronomer, all that can be seen are essentially static, unchanging states. A distant galaxy appears to be a completely motionless structure. A central supermassive black hole appears totally dormant. The interstellar medium appears perfectly homogeneous. There is simply no way to perceive, within the span of a single human life, the continuously pulsing interchange of matter and energy that is actively occurring. It is exactly like trying to fully understand the changing seasons of the year by observing the outside world for only a single, brief second. The underlying process absolutely exists, but the temporal observation window is just far too narrow to possibly reveal it. Over the course of centuries, the slightly faster changes slowly begin to become visible. A brilliant new massive star is born and in just a few short million years will violently explode as a supernova. This is a timescale that theoretical astronomy can easily calculate, but which no single human civilization could ever possibly observe directly in its complete entirety. The full physical effects of a single supernova on the surrounding interstellar medium, the intense heating, the heavy compression of neighbouring gas clouds, the possible triggering of entirely new star formation in the regions heavily compressed by the expanding shockwave, all of these effects slowly unfold over tens of thousands of years. In a span of centuries, you would easily witness the initial blinding explosion. But the complete, lasting legacy of that single explosion would take a time period 100 times longer to fully manifest. Over millions of years, the grander patterns finally become clearly visible in all their majestic glory. A large galaxy that has successfully absorbed a much smaller companion will have completely finished the messy merger and will slowly begin to reorganize itself into an entirely new structural shape. The intense burst of star formation initially triggered by the violent merger will have completely burned itself out. The highly massive stars that were rapidly born during that starburst will have all exploded, heavily enriching the surrounding interstellar medium with heavy elements that the very next stellar generation will eventually incorporate into their own newly forming planetary bodies. The central supermassive black hole, heavily fed by the massive torrent of gas that the merger forcefully channeled directly toward the galactic core, will have briefly shone brilliantly as an active quasar and then completely faded back into dormancy once again. Over millions of years, the complete full cycle of a major galactic perturbation can be clearly traced from its very beginning all the way to its absolute end. Over billions of years, you finally get to witness the grand secular evolution of the entire observable universe. The overall cosmic rate of star formation, which reached its absolute peak roughly 3 billion years after the initial Big Bang, will continuously and steadily decline. Individual galaxies will gradually exhaust their vital internal reservoirs of cold gas. Supermassive black holes will become increasingly dormant as their available fuel supply steadily diminishes. The universe, which during the peak era of its history shone incredibly intensely, with the bright light of countless stars being born in massive profusion, will progressively become much quieter, significantly darker, and far more sparse in terms of dramatic new events. The cosmos operating in its highly intense mode is a phenomenon that now primarily belongs to the deep past. We currently live in a universe that has already passed the absolute peak of its creative exuberance, and which is now slowly, inevitably marching toward a much calmer, quieter era. It is entirely within this broad context that the extreme sensitivity to initial conditions acquires its full, heavy weight, the specific universe that we currently know and inhabit, with its galaxies intricately distributed in long filaments and vast sheets surrounding immense empty voids, with its very particular current rate of star formation, and with its supermassive black holes of highly specific masses sitting at the centres of galaxies of highly specific sizes, all of this depends in an incredibly delicate way on the exact physical conditions established in the very first instance, immediately following the Big Bang. Even tiny variations in the exact density of the primordial quantum fluctuations that served as the initial seeds for the entire cosmic structure would have inevitably produced a substantially different universe, a slightly higher density in the specific regions that would eventually become the very largest galaxy clusters would have significantly accelerated their formation, fundamentally altering the entire subsequent history of matter distribution. Conversely, a slightly lower density would have severely delayed the formation of the very first stars, significantly postponing the chemical enrichment of the cosmos, and perhaps making the formation of solid rocky planets highly unlikely during those first few billion years. This represents the fundamental hard limit of human prediction when it comes to dealing with massive cosmic systems. It is not merely that we currently lack sufficient observational data, although that is certainly also true. It is that the inherently chaotic nature of many of the physical processes involved causes incredibly tiny errors in the initial conditions to amplify exponentially over vast stretches of time, accurately predicting exactly where a specific molecular cloud will collapse to form a specific individual star at one exact moment in the future is entirely equivalent, in terms of sheer computational difficulty, to trying to predict the exact daily weather with perfect accuracy many months in advance. The broad general principles are completely understandable, but the highly specific, detailed outcomes remain inherently unpredictable beyond certain temporal horizons. And yet, there is a very particular, profound beauty hidden within this limitation. There is something deeply contemplative about fully recognizing that the cosmos is simultaneously radically comprehensible and radically surprising. It is comprehensible because the fundamental physical laws that govern it are perfectly stable, entirely universal and mathematically precise. The exact same gravity that causes a simple apple to fall downward toward the Earth also causes a vast cloud of interstellar gas to collapse inward to form a star, and causes an entire merging galaxy to plunge violently toward another. The exact same nuclear physics that scientists carefully study in controlled laboratories right here on Earth is the very same physics that continuously fuels our Sun and all the other countless stars across the universe. There is a profound, underlying unity in these laws, a deep consistency that cleanly cuts across all conceivable scales of space and time, and which makes it entirely possible, at least in principle, to deeply understand events that occurred billions of years before any conscious mind ever existed to observe them. And it is deeply surprising because these exact same simple laws, when applied to highly specific initial conditions over truly immense scales of time, produce an astonishing richness of complex phenomena that no single mind could have ever possibly anticipated purely deductively, starting only from the basic principles. That gravity, combined with thermodynamics and nuclear physics, mixed with the very particular density of the primordial universe, would eventually produce grand spiral galaxies with elegant arms sculpted by density waves, would produce tiny neutron stars spinning hundreds of times per second, while emitting sharp radio pulses with the exact precision of an atomic clock, and would produce complex planetary systems where sufficient chemical complexity would eventually emerge to actively contemplate its own ultimate origin. None of this was explicitly written into the foundational equations in any obvious way. It simply emerged. It naturally arose from the continuous interactions. It was a magnificent surprise that nature itself carefully prepared for itself over the course of 14 billion years of silent, continuous elaboration. This inherent tension between the absolute simplicity of the foundational laws and the staggering complexity of the final results is perhaps the single most philosophically provocative characteristic of the entire cosmos. You can easily write down the mathematical equations describing gravity on just a single line. You can write out the complex equations describing fluid dynamics in just a few more lines. You can clearly state the core principles of nuclear thermodynamics in one short paragraph, and yet, from just those few short lines, when left to continuously act upon matter and energy over a sufficient amount of time, absolutely everything emerges. Every single supernova, every brilliant quasar, every massive filament of galaxies stretching across hundreds of millions of light years, every glowing nebula shining with the bright light of a newly born star deep inside it, every subtle gravitational wave travelling through the very fabric of space-time like an imperceptible tremor, until it is finally detected by instruments of extraordinary precision. All of this vast complexity is the direct consequence of basic principles that can easily fit onto just a few pages. But at the exact same time, absolutely no being with access only to the raw mathematical equations, completely lacking the actual experience of having observed the physical cosmos unfolding over time, could have ever possibly imagined these specific results. The equations allow for possibilities, but they do not strictly prescribe them. They open up a vast space of potential outcomes, but they do not explicitly state exactly which possibility will actually realize itself in which specific location and at which exact moment. The universe actively chooses, if we can even use that word without falling into excessive anthropomorphism, entirely within the physical space that the laws allow, and the specific choices it has made over the course of 14 billion long years have ultimately resulted in a cosmos possessing a structural and historical richness that continues to genuinely surprise even those dedicated scientists who have spent their entire lives studying it. There is a very particular deep silence that gently settles in when you contemplate this grand reality in a much calmer way, completely without the anxious urgency to constantly classify or explain everything, and entirely without the pressure to quickly arrive at a final conclusion. The cosmos is simply here. It holds 14 billion years of deep history firmly sedimented into every single atom of every physical structure we can possibly observe. Every single galaxy is a historical record, every star is a specific date written in code, every heavy element is a silent, enduring testament to ancient stellar deaths. We are, at this exact moment, sitting deep inside a system of almost inconceivable complexity, and at the exact same time, we are physically made of the exact same basic ingredients that this very system painstakingly produced over immense eras of time. We are definitely not external observers looking in on the cosmos. We are one of its direct physical consequences, and when this profound perspective finally settles in calmly, when the initial dizzying vertigo of the sheer scale and complexity gently gives way to something much more serene, something subtle slowly begins to insinuate itself beneath all this vast multiplicity of forms, processes, and temporal scales. A deep, underlying sensation that right behind the sheer profusion, far beneath the complex web of interactions, feedback loops, and connections spanning across billions of light years and billions of years, there exists something of an almost disconcerting fundamental simplicity. Something that beautifully unifies not just the physical laws, but the deep philosophical questions that those laws inevitably cause to arise. A single, unifying common thread that runs cleanly through the entire journey, from the very first instant right up to the final glimpse, and which might just be the absolute most important thing that this entire long journey through the deep time of the cosmos has to reveal. This subtle thread that insinuates itself beneath absolutely everything is not a rigid law written down in some old book. It is not a mathematical equation permanently carved into stone, and it is not even a simple concept that human language can easily grasp and hold on to. It is much more akin to a slow, gradual perception that gently arrives, much like the soft light just before dawn, when the sky is not yet fully day, but is also no longer completely night, and something fundamental shifts in the very quality of the silence all around you. The grand cosmos, with all its vast expanse of spiral galaxies, drifting hydrogen clouds and cascading epochs of time stretching far beyond any human intuition, seems to peacefully rest upon something incredibly simple: differences. The universe, in all its majestic grandeur, is ultimately nothing else but the tireless, continuous unfolding of differences, constantly finding new pathways to equalize themselves, and which, along that long journey, physically construct absolutely everything that exists. Think about the heat that naturally flows from the hotter place to the colder place. Think about the physical density that smoothly slips from where it is higher to where it is lower. Think about the pressure that naturally redistributes itself, the electrical charge that constantly seeks perfect equilibrium, and the chemical concentration that steadily dilutes until both sides of a permeable membrane perfectly resemble one another. Every single one of these physical processes is simply a difference actively resolving itself, a tension steadily unwinding, a gradient smoothly walking toward total homogeneity. And what is truly astonishing, what possesses an almost unsettling, profound beauty, is that the entire staggering complexity of the cosmos emerges precisely from this basic effort. Not in spite of it, but entirely because of it. The universe simply would not have any stars if there had not been slightly denser regions and slightly less dense regions within the primordial clouds of gas. It would not have any solid planets if there had not been distinct variations in temperature and chemical composition across the spinning accretion disks. It absolutely would not have life if there had not been sharp gradients of chemical concentration actively crossing lipid membranes in primitive, ancient oceans beneath a sky that did not yet even know what oxygen was. This deep perception actually has a highly technical name in physics, which is the second principle of thermodynamics, but the dry name completely fails to capture the true profound depth of what it actually describes. What it fundamentally states, in its most naked, raw form, is that isolated physical systems naturally tend to lose order, that overall disorder strictly increases with time, and that physical gradients inevitably dissipate. And this sounds, at first quick glance, like a depressing narrative of steady decline. It makes it seem as though the universe is simply slowly forgetting itself, steadily losing all the vital tensions that make it interesting, and blindly walking toward a final boring uniformity where absolutely nothing else ever happens. But what the earlier parts of this long journey slowly began to reveal, and what is now deeply deepening, is that this long path toward total equilibrium is not a straight, direct line. It actively detours. It gracefully folds back upon itself. It creates beautiful, swirling eddies of complex order right in the very middle of the massive flow of increasing disorder. And those temporary eddies are absolutely everything that we currently know and deeply love. Molecular chemistry is perhaps the exact place where this grand paradox becomes the most clearly visible and deeply intimate. When individual atoms bond together to form complex molecules, they naturally release energy. That specific release is simply the universe actively resolving a difference, an electromagnetic tension between opposite charges that have finally found a much lower, more stable energy configuration. But the specific molecule that arises from this atomic encounter is an entirely new structure, a distinct entity possessing completely new properties that the isolated, separate atoms absolutely did not possess before. Carbon all by itself does not breathe. Oxygen all by itself does not think. Nitrogen all by itself does not dream. But when these basic elements arrange themselves in exactly the right way, guided by nothing more than the fundamental electromagnetic laws governing how electrons distribute themselves around atomic nuclei, something entirely new emerges that actually does all of those things. Emergence, which is that specific process by which the whole successfully acquires properties, completely absent from the individual parts, is neither magic nor some insoluble mystery. It is pure geometry. It is the exact physical shape that the atoms assume when they find the lowest energy configuration, and how that specific shape actively creates brand new possibilities for interaction that simply did not exist before. The simple water molecule is a perfect example that seems entirely trivial until you examine it very closely. Two small atoms of hydrogen and one larger atom of oxygen, bound together by common electromagnetic forces, produce a slightly angular, highly asymmetrical geometry that unevenly distributes the electrical charges across the entire molecule. This distinct asymmetry causes individual water molecules to strongly attract one another in a very particular way, constantly forming transient shifting networks of hydrogen bonds that rapidly break apart and reform hundreds of billions of times every single second. And from this single emergent property, which absolutely does not exist in either isolated hydrogen or isolated oxygen, entirely extraordinary things arise. The high surface tension that easily allows certain small insects to effortlessly walk across the surface of calm lakes. The strange expansion anomaly that causes solid ice to float instead of sink, safely protecting vulnerable aquatic life beneath frozen layers during long, harsh winters. The incredible ability to easily dissolve ionic substances and actively transport them deep inside living biological cells. All of this is pure geometry. All of this is just a basic difference in electrical charge manifesting itself at the tiny molecular scale and powerfully resonating all the way up to the massive scale of entire ecosystems. The universe operates in exactly this same fundamental way across absolutely all the scales that we currently know of. In massive galaxies, it is slight differences in gravitational density that slowly sculpt grand spiral arms over the course of hundreds of millions of years. In individual stellar systems, it is extreme differences in temperature and pressure that sustain continuous nuclear fusion for billions of years before thermal equilibrium finally imposes itself and the star inevitably changes its physical phase. In the ancient, primitive oceans, it was sharp differences in chemical concentration actively crossing lipid membranes that successfully fueled the very first basic metabolic reactions, and deep inside every single living cell existing today, at this exact very moment, while you actively listen to these specific words, it is tiny differences in electrical potential, rapidly sweeping across neural membranes that physically construct what we call thought, sensation, and conscious awareness. The physical scale constantly changes. The underlying principle strictly persists. And when you carefully look at the cosmos as one single, fully integrated system, what clearly emerges is a vivid picture of continuous feedback loops firmly anchoring themselves into one another like heavily interlinked chains. The physical processes that actively amplify, which are commonly referred to as positive feedback loops, are entirely responsible for all the grand creative leaps of the universe. A massive cloud of gas that begins to collapse inward under its own gravity rapidly heats up its dense center, and that increasing heat steadily raises the internal pressure. But if that outward pressure is simply not sufficient to halt the inward collapse, the cloud continues contracting, the center continues heating, right up until the core temperature finally crosses the critical threshold for nuclear fusion, and a brand new star is born. This is a physical process that actively feeds upon itself, steadily amplifying the initial difference right up until it successfully produces something qualitatively entirely new, in exactly the same way when the very first complex molecules capable of self-replication originally emerged in the primitive oceans. Every single successful copy produced actively increased the statistical probability of even more copies being produced, creating a powerful positive feedback loop that eventually led, over an almost inconceivable span of time, to the massive proliferation of life all across this planet. But the universe is also absolutely replete with stabilizing feedback loops, which are commonly called negative not because they are inherently bad, but simply because they actively oppose external perturbations and successfully keep physical systems safely within the specific ranges that allow for their long-term continuity. A main sequence star, much like our Sun, is a living, dynamic equilibrium perfectly balanced between the inward gravity that desperately wants to contract it and the outward radiation pressure that constantly wants to expand it. If the core happens to heat up just a tiny bit more than usual, the nuclear fusion rate slightly increases, the outward pressure increases, the star expands just slightly, the core subsequently cools back down, and perfect equilibrium is fully restored. This specific system has successfully maintained its stability for more than 4.5 billion years, not because it is completely rigid, but precisely because it is highly responsive, because every single perturbation reliably generates an automatic correction. Biological life does the exact same thing at the molecular and organic scale. The human physical body carefully maintains its core temperature, its blood glucose level, and its delicate acid-base balance, entirely through complex chains of negative feedback that constantly monitor and continuously correct. You do not need to consciously think about any of this. The physical system thinks for you, because this specific type of automatic thinking is vastly older than anything that the conscious mind is currently capable of doing. What all of this ultimately reveals, when you allow your vision to expand wide enough to encompass the entirety of the journey, is that the cosmos is definitely not just an empty stage where physical things merely happen. The cosmos is the very active process of happening itself. There is absolutely no fundamental separation between the empty space and the physical structures that inhabit it, between the mathematical, physical laws and the actual phenomena that they successfully describe, or between the flow of time and the specific events that completely fill it. Absolutely everything is just one single, highly integrated system, continuously folding back upon itself across scales ranging all the way from the tiny Planck length, which is the absolute smallest distance that holds any physical meaning, right up to the massive radius of the observable universe, which is the absolute largest distance that light has successfully travelled since the very beginning of everything. And within this single system, highly complex patterns are never artificially added from the outside. They naturally emerge from deep within, exactly like delicate snow crystals spontaneously forming from pure water by strictly following simple physical rules regarding how molecules attract each other at very low temperatures, entirely without any conscious architect choosing the specific shape of every single individual flake. Deep down at its very core, the cosmos is simply the concept of difference, constantly finding new pathways to become sameness, along with the completely inexhaustible richness of physical forms that those specific pathways naturally assume over vast stretches of time. Every single galaxy that the earlier parts of this long journey carefully contemplated is ultimately nothing else but a tiny primordial difference in density that successfully found its way through billions of long years of gravity, merging, exploding, and rebuilding. Every single star is simply a massive difference in temperature fiercely burning in a temporary delicate equilibrium. Every single planet is just a distinct difference in chemical composition that slowly sedimented itself into solid layers. Every single living being is just a sharp difference in molecular concentration that successfully learned how to actively maintain its difference for a brief time, using the continuous flow of energy to temporarily delay the final, total equilibrium. And every single thought, every physical sensation, every brief moment of conscious awareness that naturally emerges while you actively listen to these exact words is just a tiny difference in electrical potential rapidly travelling across complex neural networks that the universe painstakingly built over immense eras specifically so it could finally look back at itself with blinking eyes and a beating heart. You are that specific, beautiful difference that finally learned how to recognize itself. You are the exact physical location where the grand cosmos gracefully folded back upon itself and quietly asked exactly how it managed to arrive here. And right now, in this exact peaceful moment, that deep question can finally rest. Not because it completely lacks an answer, but precisely because the true answer is currently everywhere all around you, in every single deep breath that actively brings star-forged oxygen deep into lungs that originally emerged from ancient primordial oceans, and in every single steady beat of a heart that is the very distant direct descendant of the very first molecular pumps that rhythmically pulsed inside simple single-celled organisms billions of years ago. The ultimate answer quietly resides in the deep silence that naturally exists right between the spoken words. You are completely safe. The vast universe that carefully constructed every single atom of your physical body over a span of time that the conscious mind simply cannot fully grasp, intimately knows the exact pathway back to perfect equilibrium. And that specific pathway passes directly through deep rest, through peaceful sleep, and through the profound, regenerating silence. While you peacefully rest, the distant stars silently continue their steady fusion, continuously converting light hydrogen into heavier helium with a profound patience that absolutely no human word could ever adequately describe. The grand galaxies smoothly continue their slow, majestic spiral dance, a dance so incredibly slow that no single human life would ever possibly perceive even a single degree of physical rotation. The massive clouds of interstellar gas patiently continue their slow coagulation, quietly building the very next grand generations of bright stars that will be born long after any living memory of any human name has completely faded away. The grand universe definitely does not stop just because you gently close your tired eyes. It simply continues being exactly what it has always been. The fundamental difference constantly searching for sameness, the vast complexity naturally emerging from simple underlying rules, and the deep time continuously deepening physical patterns that originally began long before there ever existed a solid planet where someone could actually name them. You are an integral part of all of this. You always have been. Every single biological cell inside your physical body deeply carries this grand history, firmly inscribed in complex molecules that perfectly folded themselves in exactly the right way, specifically so that you could exist right now, right here, in this deeply deserved moment of rest. Absolutely everything is perfectly in order. The fundamental physical law that tightly governs the electrons orbiting around atomic nuclei is the exact same law that originally governed the formation of the very first stars. The natural law that gently guides the flowing water down to the vast sea is the exact same law that powerfully guided the primordial matter into the very first galaxies. You are currently sitting deep inside these physical laws. You're entirely made of them. They are fully sustaining you right now exactly as they have perfectly sustained absolutely everything that ever existed long before you. The vast universe actively cares for you in the very only way it physically knows how to care, by strictly maintaining the fundamental physical constants at the exact precise values that allow individual atoms to bind together, that allow complex molecules to fold correctly, that allow physical hearts to steadily beat, and biological lungs to deeply breathe, and that allow conscious minds to finally rest. Gently allow all the busy thoughts of the day to smoothly dissolve away, just like physical gradients that have finally found their perfect equilibrium. Gently allow the physical body that was carefully constructed by ancient stars to finally find the deep rest it so richly deserves. Gently allow the heavy weight of all your deep questions to softly settle down, entirely without urgency and completely without any rush. You are completely safe in this exact moment. The grand cosmos that took an absolutely immeasurable amount of time to carefully construct every single physical particle of exactly what you are is definitely not going anywhere while you peacefully sleep. The distant stars quietly continue shining brightly, far beyond the dark clouds that you simply cannot see right now. The deep time quietly continues smoothly unfolding in absolutely every direction, remaining just as tranquil as it has always been. And you, the small, extraordinary physical consequence of a vast universe that finally learned how to recognize itself, you can completely rest now. Completely. With deep peace. The vast universe quietly continues its silent, majestic dance, and we peacefully rest securely within its warm embrace. Thank you so much for walking alongside me this evening. Sleep very well.